Oh, it's recording already. Hi guys, my name is David and today I will be teaching you about propositional logic. Now, you might be thinking, wait a second, where's your traditional whiteboard or chalkboard that you stand in front of? Well, it's because I got this new drawing tablet that I'll be using to teach videos from now on. It saves me the time of not bringing my tripod and everything to school and finding a random classroom, so I had the luxury of teaching in my own room now. And if you're wondering why I'm wearing this hat, it's because my haircut sucks, so let's go! So a quick recap of the last video. P is a predicate or property that is evaluated to be true or false with given input. We mainly denote predicates in capital letters, starting with P usually, and P of X is read as X is an object that satisfies property P. So a boring example I'm going to use is I'm going to define the predicate P to be the event where the object X is an even number. And as you know, P of 2 would result in true, and P of 3 would result in false. And I'd like to remind you that P of 2 and P of 3 are known as propositions. Statements that are actually true or false. So now we're going to be looking at propositional operators that will allow us to form new predicates from the previously existing ones. So these operators are also known as functions and can be linked with the machine analogy I used from the last video as well. Okay, so the three operators that we'll be talking about today is the AND operator, also known as the conjunction operator, or disjunction, and NOT, which is known as the negation operator. So using the machine example again, this is the conjunction machine. Now the thing about this machine is that it requires two inputs to work. This is also known as a binary operator. So when you put two predicates in here, both of them have to be true for this machine to output a result of true. And the notation for conjunction, or the AND operator, is this upside down V symbol over here. So these two are actually equivalent. So to kick off this example, I'll be using English statements only. No complicated math or numbers at all. Alright, so here's the masterpiece. We have four people here. This handsome young man, known as David Pham. Stephen Tran, a good friend of mine, with a really interesting profile picture on Instagram. You should definitely go follow him. It's getting a bit hot in here. Sorry. Another great friend of mine, Rain Wu, and I don't know who this guy is. But in this example, they either like or dislike fried rice or noodles. So I've defined two predicates here, P and Q, where P is the event that someone likes fried rice, and Q is the event that someone likes noodles. So we're going to define David as someone who loves fried rice and noodles. I like both of them. Come on. David likes noodles on Instagram. You know, Steven, he likes fried rice, but he's not a big fan of noodles. That's a big X. Rain doesn't like fried rice, unfortunately, but she likes noodles. And Ali doesn't like either. Not a big fan of Asian food. I'm also going to add in one more definition, and that is a propositional variable. So a propositional variable basically represents a proposition, because sometimes we're too lazy to write out P of David or P of Stephen, etc. And by convention, propositional variables are the lowercase version of the predicate. So in this case, just lowercase p and a lowercase q. That's what we'll use. We'll get into that later. So let's start with me. If I put P of David and I put Q of David, so if we put those two into the conjunction machine, we actually get a result of true. Why? Well, it's simple. I like fried rice and I like noodles. And as I said before, the only time this will spit out true is if both the propositions that you put in are true. Let's move on to Stephen. So P of Stephen, I'm just going to denote that with a lowercase p. This is true. This is true. He likes fried rice. But Noodles, Q of Stephen, or just a lowercase q, unfortunately that's false. When you put a true and a false in the conjunction machine, it's actually going to spit out false. Same thing for Rain over here. She doesn't like fried rice, but she likes noodles. But once again, there's one value of false in that machine and it's going to spit out false again. And for Ali, we have a double negative, and sadly that does not equate to a positive, and that's just going to result in false again. So if that was a bit complicated or somewhat overwhelming, we can organize this data in a truth table so that we can quickly and easily observe the structure of each logical statement. That's what the truth table looks like in its entirety. Oh, I completely forgot to translate the statements for you guys. So if you're wondering what the translated English version of P of David and Q of David mean, it's equivalent to saying David likes fried rice and he likes noodles. And I'll leave the rest for you to interpret yourself for the other three guys. So next we have the disjunction operator. Again, this is a binary operator, so you need to input at least two predicates for it to output another one. The disjunction symbol is essentially a V, and as long as one of the predicates that you input is true, it will output true as well. So let me translate one of the statements first. So P of David or Q of David translates to David likes fried rice or David likes noodles. So let me just erase this real quick. And again, we're going to use the propositional variables because I'm lazy. So once again, we're going to start off with me here. I like fried rice and I like noodles, and that's going to output true. Now, this might be offsetting to some people. For example, if you ask someone in person if they wanted fried rice or noodles, right? You'd expect them to pick one and not both. That would be a bit weird. But in logic, as long as one of these statements is true, then we get a result of true. In computer science, it's very similar. If you have an if clause or something that requires at least one condition to be true, as long as that's satisfied, it will also process as true regardless of how many conditions were satisfied in the first place and proceed with the code. So regardless of how many things I like in this case, it will output true. So let's move on to Stephen. He does not like noodles, but he likes fried rice. And this time the machine will actually output true because he likes at least one thing, so it's going to output true. And same thing for Rain, right? Her tastes and Stephen's tastes are quite the opposite, but she does like something, which is noodles, and that's going to output true again. However, when we get to Ali, he doesn't like either. Man, what kind of person dislikes fried rice and noodles? Like, what? But anyway, he doesn't like either of them, so that, when you put that into the machine, that's actually going to output false, and that's the only thing that's going to output false. So when we do the truth table, that's what it looks like. So the last thing we're going to talk about is the negation operator, or not. Now this is a unary operator. This actually only needs one input for the machine to work. And it's a bit different. What the not operator does is it spits out the contrary of what you had put into it. So let's say P is equal to P of David again. David likes fried rice. If you put P in here, then what it's going to do is it's going to output not P. So lowercase p was David likes fried rice. Not P, translated in English, would be David does not like fried rice. Oh my gosh. Me not liking fried rice is unthinkable. That statement's false. Let's say lowercase p was now p of Ali. Hi guys, this is David from the future. I'm here to tell you guys that I actually messed up this part of the question. I didn't explain it properly and the interpretation is actually incorrect. So what I did here was that I put the proposition p into the machine. The propositional variable p is currently equivalent to Ali likes fried rice. And that is false because we know we defined initially that Ali does not like fried rice. So when you put that statement in the machine, you'll get Ali dislikes fried rice. And that part is true. So again, the whole concept is putting something that is false into the machine and then making it output something that is true as a result. Thank you. So the truth table is a lot more simple now. If you negate something that's true, you're going to make it false. And if you try to negate something that's already false, then you're going to make it true. So before I end this video, there's actually one more thing I'd like to bring up, and that's when you have multiple predicates at once. So for the and or operators, you can actually put more than two inputs if you wanted. Say we had something like this. The only way this can be true is if lowercase p, lowercase q, and lowercase r are all true. That is when this will result in true. Otherwise, it's false. For lowercase p or lowercase q or lowercase r, if at least one is true, then this will output true as well. The only way this can be false is if all the propositional variables are false. Expand here. Thank you all so much for watching. I left some homework, as always, in the description for you guys to try out. And I recommend that you actually do try it. There are a lot of exercises this time, just so you can get the feel, get the hang of propositional logic. The next one will be even more complicated. Feedback would be nice as well. If you have any suggestions or you just want to ask me anything, suggestion box will be in the description as always. Thank you very much for watching. I'll see you guys in the next video.